Hello, my name is Alessandro Nardini and I'm working in VFX for film, TV and television for about 15 years or something. And today I'm going to show you something very useful. I'm going to show some example of destruction that I've been doing in the past. Those are has not been done with Houdini, but the technique that have been used to do to achieve certain aspect of it, they're actually the same, and we're gonna see today how to transport that inside Houdini. So the things I want to show you is what I call a smart activation. So we do have this road that has been prefragged, and those two chunks they are moving apart from each other, and all those in-between chunks, let's call them the way, they are automatically activated based on the distance between the two original chunks. So basically what is happening here, we can see very well over here, is that those chunks and those chunks, they actually belong to a way bigger chunk. Let's call them chunk 1 and chunk 2. And all the tiny chunks that form the edges, they look around them for other chunks, and if they find a chunk closest to them, they live on a different bigger chunk, they form a partnership, a relationship. And that relationship is basically the initial distance. And once they move apart from each other more than a certain amount that we will decide, those chunks will get activated and so fed into the rigid body solver. And so you will make all the simulation be driven by the original single two chunk animation. And so that is also a good way you can use to iterate through animation department and dynamics, since the animation is actually driving the whole setup. And there are other examples. The ground here has been done with the same concept. Has been preflagged. In this case, this one is just Voronoi, and then the animation of the main big chunk has been done by animation, and then once the system is up and running in dynamics, we can just play, and based on distance and velocity of the original chunk, the in-between chunk get activated and fed into the rigid body solver. And this one is another example. So this, again, all those geometries being prefragged, and once the main big chunk has been generated, chunk by chunk get apply a procedure to fragment all the edges, and then all those edges, all the edges get applied this procedure, which based on the original big chunk animation, they decide if they get activated or not. And if they do, they get decided for which velocity they must use and what spin and so on and so on and so on. But everything uses the same concept. And so it's a very cool method to use that will speed up also the iteration process and will make it also very believable, like this piece. So we will do it in Houdini. So we will do something simple like this kind of extruded plane or big box. And we will end up with a few chunks to make it fast to work on, just for tutorial purpose. And those chunks will have a name. In this case is piece 1, 2, 3, 4 until 10. And if we look closely, those are actually the same chunk as those. And so we will see that all those edges, they are actually fragmented. In this case, I'm using Voronoi, but usually, and especially now that a very cool tool came up, and this HDA for Houdini that Taz, a friend of mine, that worked at Weta, Scanline VFX, very talented FX artist and TD. The way it works is that the geometry visually. And so the same concept has been used for those distraction. We have been using a very similar tool, but not for Houdini, to actually prefrag the geometry in advance and then apply the procedure on a second step. The concept is this. Once we have all the fragments done on the edges, in this case I'm using Voronoi for speed purpose, they will be packed in a package geometry, and so those black points represent the pivot. And then we will run through a point cloud iterator, and for every piece, in this case is this one that has been highlighted with this color, we look around itself within this radius and it will find all those other pieces. And all the pieces that we do not want, are the pieces that are living on the same bin chunk as we do. And so all those pieces will get skipped. But once we find the closest point that live on a different chunk, in this case piece 8, while us are living on piece 01, we will establish a connection, which is simply a distance. And that connection will tell us which piece is partnering up to which other piece belonging on a different chunk. And so two pieces of two different edges. And then this is somehow the result. You will get some sort of stitch all along the edge that are binding pieces from different chunks. And this one is what we will end up with. Once we have that, we could check this distance every frame at simulation time. And if the distance increases of a certain amount, we will know that just there those edges are breaking. And so right at that moment, we are going to activate those pieces and fed them into the rigid body solver. Okay, so let's open Houdini and let's do it. I'm using Houdini 17.5 Indie, version build 173. Let's create a geometry node and let's call it smart activation. I assume, before we proceed, I assume you know Vex, I assume you know a little bit of DOP, and I assume, of course, you know SOP. So let's start. Let's build a box. Everything I'm doing now is to generate a simple case scenario in order to have the data necessary to apply the smart activation algorithm. So I'm not gonna stop on every step by step and explain everything I do, as I assume you know and you will follow easily. But in case you will find certain step not easy to understand anyway, just leave a comment and I will be happy to reply. So let's do a box 10, 0.5, 10, and let's make some sort of square wall. Let me make the background dark, hide the grid, I like it better. So we're gonna break it, this object in, let's say, 10 chunks. Lay down a nice offset, that's good enough. Let's scatter some point. And we say about 10. And let's use a Voronoi fracture. First input is the geo, second input as the cell guide points. Maybe let's change the global seed and find something more homogeneous. Yeah, something like this. I like it. Okay. Now let's so this will generate a name attribute per primitive level telling us the name for every piece from 0 to 9, so 10 pieces. and this will be the name we will carry on through the end because it will be very important, but you will see. Let's move this up with a transform node. Okay, maybe 10 and 30 degree should be good enough. So we will make this fall, and let's assemble, and with the first one we will generate the name. Oops. And we will clone this guy, and with the second one we will just pack it back. I'm doing this because then I can branch out and do other stuff we need from here. How to edge fragments. Okay, I usually do those black. Okay, and then here is how to dots. Okay, so let's do a sphere to collide to. Okay, and let's place this here. Let's make it a polygon, maybe 5, even 6. Let's move this up 1. Let's give it a name just to be correct for what is needed to pack a geometry. This one is a sphere, and it will be at this point for it's a point, and let's pack it. Okay, and let's gather this guy. Perfect. And this is a sphere. Okay, and this one will be a collision object. Out SPH collision. Okay, and now let's drop down a dop network, and on the first input is the wall, on the second input is the sphere. Let's dive in. Let's lay down our IG body solver. Okay, let's wait. Let's lay down a gravity node. Okay, let's lay down a packed RBD packed object, and this will be our RBD wall. And let's lay down a ground that we need to collide to. Let's merge those two, and here we got this. Now for this RBD wall, let's import the wall fragment. So OP input path, and we go up once and import the first input of this DOP. Back tip to evaluate, and here is our wall. And let's clone this guy. This will be our sphere, and let's merge those two. Okay, and this one will be input 1, and it will be a static object. And so now, okay, if we play, that's what we got. It's very cool. That's exactly what we need. Okay, so let's call it Doppler. Let's lay a null out Doppler. Make it black as always, and here let's import just the RBD wall. Okay, so we got our low-res geometry falling down and breaking, and now we're gonna create some edge fragment, and then we're gonna see how to implement the smart activation technique. So let's get the non-package geometry. since we have to modify the geometry itself, and let's lay down a for each connected piece. We don't really need the connectivity, and let's change the piece attribute from class to name, and this one will be in piece, so the single one coming into the for loop. Okay, and let's delete the inside faces, which we don't need. So inside, delete and unselected. Let's keep only the outside, and let's scatter some point to it, like so. Maybe 250. Let's increase the iteration here. Something like that. And let's VDB from particle. Okay, so we create a little volume out of it. Something like so. And let's lay down a volume bob, and let's perturb this volume. Turbulence noise. Let's plug the P. And let's multiply the incoming density by this noise. And let's promote a few of those. That's enough. Okay. And maybe here a little bigger. 1.3. Let's increase the amplitude. Okay. And now let's scatter some point inside here. Okay. And let's go inside the volume bob and contrast a little bit the output of it. So, and let's promote parameter, and let's set it to 4 maybe. Yeah, that's good. Maybe a little less, 3.5. Yeah, I like it. Okay, let's lay down a Voronoi fracture. Let's plug in the original geo coming into the loop, and let's fragment it using those points. Perfect. Maybe we can increase a little bit. It will be a little slow to process all 10, but we're gonna bake it just after, so it's okay. Okay, I like it. That's very good. Now, once we Voronoi this piece, which is one of the 10 we need to process, this piece originally came in with a name attribute, and in this case is piece 0. But once we fragment it further, the new Voronoi will generate a new name attribute that belong to every one of the single pieces, so they will get enumerated. What we want to carry on this name attribute originally we had and transfer it to all the new pieces. So we can do that with an attribute copy, and let's plug this here and this here, the geometry we want to copy from. And actually it's the very opposite. Okay, and we don't want to match the P attribute, and we want to copy the name. And so now if we look, everyone has the same name as the chunk that is coming into the loop. And that's exactly what we want. One thing we want to promote this to point level and change the name, since we're going to generate a new one later on. And so let's lay down an attribute promote. Okay, and we want to promote from primitive to point, and we want to change the name and then eventually delete also the original one. And let's call it name old. Okay, and let's process this. So 1, 2. I wanted to do a little bit less pieces just to go fast, but since we are doing it, let's do it so we get some nicer result out of it. And it should be fast enough. We are already a little over half, 7 out of 10, 8 out of 10, 9, almost there. There you go. This is good enough. So now what we want to do, let's lay down a null, or I do lay down a null out for iRes. Okay, and let's bake it. Okay, so we are almost there. One thing we need to do, we need to generate a new name attribute, because now we got name old, and name old tell us that every one of those pieces. Let's assemble this first. Okay, and let's carry on the name old. So every one of those pieces, since now they are package geometry, they belong to piece 0. So we are talking about all of those, they have the same name, old value as the same name as the chunk they're coming from. On top of that, we generated a new name attribute which actually enumerate them. So cool. Now let's start to implement the smart activation algorithm. First things first, we need to create an attribute which will be the ID of every piece. And so to do it, we do an integer attribute. I call it piece ID, and it will be the same as the point number. Okay. And so now we get this, which is exactly what we need. Okay, so this one is piece ID. Let's make it this capital. Okay, so now we do another wrangle where we will do mostly the hardest part of the job, and this will be the smart activation. Actually, not even, it will be partnering up. Okay, so the first things we will do, we will find a closest partner that is not living on the same chunk. Okay, so there are a little things that I always do is more of a convention. Every time I have an attribute that I want to use inside the code, I usually remap that attribute to a variable and use it. So I can save the typing of for example, if it is a string, like in this case, and let's call it my chunk. I will remap it to this. Okay, so I won't have to type every time I have to use it as at, but I will just type my chunk, and this variable will hold this attribute value, which in short will tell me which original big chunk they are coming from. Okay, now next things we need to do is, since we're using a point cloud mechanism, we're gonna set up our point cloud attribute. And so first we need a radius, and it will be a channel float, obviously named radius. Second, we need to tell how many points we want to consider, so it's a max point variable, and it will be a channel integer called max points. Okay, and then finally we can define an handle which will carry on the point cloud open function, and it will be from this geometry. It will look for p with those value. Okay, and it will use this radius within this distance, and it will try to find as many points as those max points. Okay, let's create those, and let's set the radius to 1 and max point to 100 just for start. Okay, so let's define an attribute called partner, and let's set it to -1. and let's define some variable we will need later. So first of all, we want to know which chunk the pieces we find around us through the point cloud belong to. And so we will store that information inside here, and for now it will be just an empty string. And let's remap also the piece ID inside this integer variable, so piece ID, which is the one we defined up here. And then let's here I went a little too much. And then let's define some variable we will use later. So let's call it order ID. Let's set it to 0, and then let's do order PT. Let's set it to -1, and then let's set count for our loop, and even this one, let's set it to -1. So at this point, we are ready to order ID, it will be whatever, so piece ID will be the ID of the current point we're processing. And inside order ID, we will store the piece ID of the point we find, while order PT will be the point number of the point we find. Okay, so let's use a while mechanism, and let's iterate through our point cloud. Okay, so first things, point cloud in Houdini, they are already ordered from the closest to the furthest, where the closest is actually ourselves. Since we don't want to consider ourselves because we have access to it already inside the wrangle, which is the point which is currently inside the wrangle, when we look around, we want to skip it. We want to skip ourselves. In order to do that, we can simply say if count is less than 0, which is currently is -1, then increase the count of 1, and that's it. And so we do nothing to us, we just keep ourselves. Otherwise, else, we want to do something to the next point, from the next point on. And so let's import some value from the point we find. So let's use PC import, and from the handle, and we want to import the name old, and we want to store it inside the other name variable. Also, what we want to import is the point number. Okay, and we want to store it inside the other PT variable. And also what we want to import to is the piece ID of the point we found. And this will be, we want to query this attribute, and we want to store it inside this attribute, this variable. Cool. So basically what we did is, from this point, we skip this point first with this little trick, setting the count to -1 and skip it if it is less, if it is -1, and just increase 1. So from now on, we're gonna get all the other points. And once we skip ourselves, we find one of the other. And once we find one of the other, we're gonna ask them, hey, you, can you tell me which is your piece ID, which is your point number, and which chunk name are you living with? Because me, myself, I'm living on piece 1. And so I really hope you are not living on the same chunk as me, because that's a reason for me not to be interested in you. But if you're living on a different chunk, for example, piece 8, then, like this guy, then I will be interested in you. And so let's do this. So the way we can do it is simply, since now we know the name so the name of the chunk of the piece we found, and we also know the name of the chunk we are in ourselves, we can simply say if my chunk is different than other name. Okay. Okay. So now if we are inside here, we found a point that is living on a different chunk. And also, since we evaluated a partner attribute to -1, that means everything that come into the loop, if it is -1, that means has not been processed. And so if this will be not -1, but it will be something else, that means that point we are currently processing is being already partnered with somebody else, and so we don't want to change it along the line. And so in order to prevent that, we're going to put this condition that we're going to say if it's okay if I'm not being processed, which is obviously -1, then we say if partner is equal to -1. Okay, then here we are going to set your partner to the other PT. Okay, so that's your partner, which is this point number. And also we're going to set some attribute on the other PT, so on the partner itself. And so what we are going to set point attribute, what we're going to set is we're going to set the piece ID. And so it will be on this geometry, piece ID. That's what we want to set for which point for other PT, and which value our piece ID. So now they will match, and we are gonna set this. Also, what we're going to set, it will be the partner, so 0, and we are gonna set that partner value for our partner, and it will be this point we want to deal with, and then the partner will be us, our point number, and then set. Okay, let's put this here, and then once we are outside here, we just keep counting for every point. We don't need to, but just to be precise. Okay, cool. Let's see if we make any mistake. Oh gosh. Now, handle, little typo. Okay, so partner, okay, name old, okay. There are way too many ones. So let's see. This ID, other PT, count, handle, name old, other name, point, number. There you go, another typo. Okay, and now there should be way more partner than not just one. Cool. So now what we did is those points that have partner -1, they are most likely the object in the chunk in the middle that they could not find, they could not reach any closest chunk that live on a chunk different than itself within a distance of 1. Okay, so the more I increase the distance and the less -1 we will get. Okay, technically it's just because at some point we are just not partnering more than 1. Anyway, if we keep this to 1 and we go here and we lay down a point wrangle and say if partner is equal -1, then remove myself. Okay. Okay, and now let's make this radius smaller. We will see that the -1, they were all the centerpieces, and all the other ones have been partnering up, so they're ready to check against each other. Okay, one more thing that we need to do here. is we need to initialize this initial distance between every chunk and its partner. And so initialize distance with closest partner. And so, as always, as per my convention, let's store it this into a variable. Okay, and then let's initialize a variable dist for distance. And then what we can do is if the partner value is higher than 0, so if you actually have a partner, then I want to know the position of your partner. So partner position is equal to point, and on this geometry, and I want to know the P, and it will be the point, it will be the partner point. Okay, and now distance, it will be equal to the distance between ourselves and our partner. Oh, position. And then later on we can do f init distance is equal to distance. Okay, so now if we look here again, am I making any mistakes? Semicolons. Okay, this something off. Okay, this works. So now what we do have is, if we look at this, so all the partner with all the points, the chunk that have no partner, obviously they have an initial distance of 0. But as soon as we get a partner, we will know how far away we are. So chunk 5919, it will have, it will be 0.08 unit away from its partner, which is point number 650. That's pretty much the concept. Okay, so now to validate this, let's create point out of both those. So let's delete the geometry and keep point. And let's lay down another add. Okay, and let's create a line between the partners. So let's say piece ID. Okay, no here, by group, by attribute, piece ID, and there you have it. So here we are at this point pretty much. So now we found a partner and we initialized the distance. Okay, so what we need to do now is, since we have this nameAll attribute, which actually tell us which big chunk every one of those small belong to, let's conform this to this upcoming lowest dop. So let's rename attribute rename, and let's rename its name to nameAll. Okay, and there you go, that's the only one we have. Now let's create a point wrangle, and let's plug the new chunk with the partner information we just calculated. Okay, which is this pretty much. And let's get the low-res simulation coming from DOP. Okay, and now let's transfer this animation to this. Okay, so what is happening now is that this simulation coming from DOP, which is the low-res, as name attribute that match, now it's called nameAll, that match nameAll that match the nameAll that we have on this one. Also on the primitive, the intrinsic value, they have information about its transformation. One of them is the transform, and the other one is the full packet transform, which is packet full transform, which is this one, which actually has everything in there, okay, as rotation and translation, and obviously scale, which are baked into the value. Anyway, what we want to do is now we want to read those transformation matrices and use them to transform those using the same name attribute. So in short, every piece that belong to, or they're coming from the same chunk, will get transformed by the relative low-res chunk. We first look from here, we look into here and find which piece have the same name old value as this piece. And so to do so, we will do an int pt, it's equal to find attribute value, attribute val. And what we will look into the second input geometry, so input 1, and it will be a point attribute, and we will look for an attribute called name old, and we want to match it against the value of our self attribute called name old. Okay, so now this integer will store the point number of this geometry that actually have the same value of any point number in this geometry. And so once we have done that, we can simply query the transformation matrices from this geometry using a prim intrinsic. And so we will start with the rotation. So it's a matrix 3, M3, it will be equal to prim intrinsic. And which prim intrinsic we want to query. So from the first input, so this input, we want to query the intrinsic called transform, and from which point pt. Okay, and then we will copy and paste this guy, and this one will be a packed full transform, and this one will be a matrix 4. Okay, so now that we stole the transformation matrices, we can even steal a few other information, for example velocity and angular velocity. So vector other v will be equal to point from the second input. We want to steal v from this point, and also we want to store the angular velocity, which is w, and it will be point, second input, it will be w, and from this point. Okay, so now we can transform it, and first of all let's set ourselves prim intrinsic. So set prim intrinsic, and it's on ourselves, and we want to set the transform and for our current number currently processing inside this wrangle, and we want to set it with the information we stored previously, so with the rotation in this case, and we want to set it. Okay, and we will see that now. Oh yeah, so sorry, we will see that now the rotation are baked, the rotation are working. Now the only thing is missing is the translation, and so we will do it with our matrix 4. Since those are package geometry and they are only point, the only things we need to do is really simply multiply this by this transformation matrix 4 times equals apologize. Okay, so now they are all moving correctly based on the low-res simulation. Okay, And now a few more things to do is to set our velocity to the other v that we stole before, and to set our angular velocity w to the other w we stored before. And so now here we will have v and w working coming from the original DOP, low-res DOP. Okay, cool. And here transfer with low-res. I don't want to do this. Okay, at this point we are here and we can see the animated high-res based on the low-res simulation from DOP and the connection between all the adjacent edges. And so the next step will be to measure those lines, and when they exceed the initial distance we stored, to mark those pieces as broken. So let's do it. Let's create another point triangle. Okay, and let's call it mark broken pieces. Okay, so let's first we are gonna create an attribute called found. It will be our marking attribute, and we are gonna set it right away to 0. Then we are gonna, as always, remap our partner, at partner. Okay, now if we look again at the partner attribute, we will see that who got a partner is a value above 0, and who doesn't is a value of -1. And so to optimize a little bit, we can check against this attribute and simply say if the partner is bigger than 0, greater than 0, and also if has never been found. Okay, then what we can do is first gather the partner position. So partner position is equal to 0.0 p of this partner point, and we can gather also its velocity. Partner vel is equal to 0.0 v and this partner point. Okay, then we can measure the distance again, and this will get checked every frame, and it's a vector, I apologize, it's a float. So float dist is equal to distance between ourselves and the partner position. Okay, and now since this distance gets calculated every frame, and since we have our initial distance here, okay, what we can say is if this distance is greater than whatever initial distance our pairs have, init distance plus a little bit, let's set it to 0.2 for now, and we will change it later. So what we can do here is first of all mark them, so simply found ++, and also let's mark their partner. So set point attribute 0 found, and of this point partner, and let's set it to 1, and let's set it. Okay, another things that we can do is to set the current point velocity, and so what we can do is set v equal to our current v plus the partner velocity, and just divide it by 2, so we get a little bit of both. Now, at this point, we should found, apologize. Okay. Now we shall have this attribute that mark the broken pieces. And so if we go ahead, we will see that they goes from 0 to 1. Now the only weird things I just noticed is that some of them are already 1. And I do believe the reason is because we are oversetting their partner. And so perhaps we can avoid to set the partner. And so let's comment this out and let's double check. So now they're good, they are 0 as they should at the beginning, and they're getting 1 after a little bit. Okay, so that's good. So now what we want to do is to finally set the Regibody attribute active. And so let's lay down another point triangle and let's call it set active and debug color. Okay. And so here what we can do is as always partner equal to y at partner. And so here we can simply say if you have been marked found is more than 0, found is more than 0. So if you have been marked, then you are going to be active equal 1, and also you are going to be of color red equal 1 0 0, and we are going to do the same also for their relative partner. And so set point attrib, and so 0, this geometry we want to set the active of this guy, and we set it to 1. And let's finally set it. Let's copy and paste, and let's set the color for the partner as well. And so this will be a red and this will be CD. Okay. So now here we can simply do an attribute promote, since they are packet primitive, and just promote color from point to primitive, so we can actually see it. And yay! Perfect. So now those got activated. Now there is a very little problem that we are going to fix, is that if we look here, some of those pieces, they get activated and they activated again because they get back very close to each other, and so the distance go below the threshold, and so they go back to not being found, and so they go back to an active value of 0. In order to fix that, we will do a little subsolver that will accumulate frame by frame, and so once they become 1, they will never go back to be 0 anymore. And so let's lay down a solver. Okay, and let's get our input. Let's create a point triangle. Let's input 1 on the first, preview frame on the second, and here let's just grab the preview frame found value. So prev found is equal to point 1. We want to get the found of every point. Okay, and then just let's add this value to the current found value. So prev found, And now, just to be safe, let's just clamp this guy to 0, 1. Oh, clamp e at found 0, 1. Okay, this should fix that. And so let's go back and check. Perfect. Okay. So now, just to test it, let's increase a little bit this distance, maybe say 1. Okay. Very cool. So now what we can do, though, is to randomize a little bit this distance per piece. And so let's build a little random threshold. So let's do it. Random threshold. Okay. Let's create a random value and be equal to this per point at ptnum. Okay. Let's create a threshold slider equal to channel float threshold. Okay. So let's create this guy. Okay. Then rand equal to channel float rand. Okay, and then let's create a min. It's equal to threshold minus rand, and then float max is equal to threshold plus rand. Okay, and now float final rand is equal to fit01 R&D between min and max. Okay, and so also to not have a 0 at the very bottom of those values, let's set this to 0.01 and a bigger value here. Okay, so let's create this. Let's set the threshold to 0.2 still. And so now what we need to do is distance is equal to this final distance plus final rand. And that should be all about it. Okay. Okay. So, okay, let's do a big number here and about the same there. Perfect. Okay, so it's working. Something like this should be good enough. Maybe not even, be a little smaller. Okay, that's perfect. So subsolver, accumulate found. Okay, so we're almost there. What we need to do now is to create a DOP network. So DOP network. Okay, IRS, and let's put this together. So tragic body solver, gravity, okay, a ground, okay, let's merge those. Okay, and then packet geometry. Okay, so this we said is our RVD wall, and let's import it up once. Okay. Okay, so now here we can say overwrite attributes, and this active value will get read from the above SOP every frame. And we can also set, since we did set its velocity over here, we can go here and set this to inherit velocity from point velocity. Okay, so we didn't set angular velocity yet, but it's just a question to set it above over here. And so let's see what we get. Oh, I forgot one thing. We need to be here and set this to animated static object. Okay. No. That should be it. Maybe why doesn't animate? There you go. I needed to reset the DOP network. Now everything gets activated automatically. It's pretty cool. Okay. So let's create a null out irs. We are almost there. A few things we still need to do is to, so we got a threshold limit, a random number, and perhaps since the velocity is just right off value from the preview low-res DOP, maybe we can float, we can add a velocity multiplier equal to channel float vel mult. Okay, so let's create it, and maybe let's set this to 2, and now what we can do, we can set the angular velocity as well. Okay, w angular, and then here we can just do this w angular, and then here we can say e at v times equal, how did we call it, vel mult, and also we can do the same with angular velocity. Okay, ang velocity, ang mult, and then here we can say v at w is equal to, times equal ang mult. Okay, let's set this to true as well. So now, just for the sake of it, let's increase this to 5,000 and let's bake it. Yep. 5,000 and let's bake it. Okay, let's watch to some playblasts to the final result with a higher setting for Voronoi and see what it looks like. Very cool. So we can see that all the in-between pieces, they get activated correctly. They have some sort of realistic direction where they shoot and rotate, and the result is very believable, and it's very cool to work on low-res geometry. In this case, it's very low-res. But if we consider that we started from here, and this is what we had, so just a bunch of very simple pieces, and with some little trick, we got to something very complex like this, and very organic too. And of course, if you prepare the geometry in advance and cut the geometry more properly, now it's just a simple Voronoi. This one is a very high-res one. It has some nice variants in it. There are some nice pieces, and also it's very good to see how the velocity that we set actually work very well when the pieces move and rotate. But if you consider where we started from and what we were working on, which was, again, this one, it's very fast to iterate through, very fast to art direct. It's just a bunch of pieces. You can even work on those separately, setting some custom velocity to make them do exactly what you expect them to do. And then just going through a very simple and short setup like we did, you can achieve something very cool like this one. And this one is another one a little more close up. So everything is taken care by the tool, and you just do the rough animation or simulation of the low-res pieces. It's very cool. And I've been using this since almost 10-15 years. I started to do this, and then I just carried this simple technique on over and over and over along the year. So this one is what the activation look like. And this one is how fast is to compute everything we did during the Houdini session. So you can literally and visually check in real time whatever the activation is, what you expect, and if not, you can just tweak it before going into the DOPS. So for example, if we want to get less of the edge, we can just go back and make a smaller radius here. We need to reset for the subsolver to pick up, and now we will have a smaller selection radius for the pieces. Okay, let's make it even smaller. There you go. A very small one. So, and yeah, so that's pretty much it. I hope you enjoy it, and hope it is useful, and hope you're gonna end up doing something very cool with this. So thank you so much, and bye bye. And take the rump to the funky beat.